Consider the case where we have a deep well and we are pumping water far away from the phreatic surface, so we are really not affecting the phreatic surface. We are pumping water almost from a far swimming pool under hydrostatic conditions in the far field. If we draw the total energy with respect to x and z, because actually when we solve the flow condition, like in a flow net, we are capturing the third dimension on the plane. Actually, this is going to be something as follows. And this is the total energy with respect to x and z, where this is x and z. Now, at the center, in the xy location of the borehole, if we look at it from the top, we would actually be seeing a flow net where all these equipotentials are projected onto the surface. And when this system reaches a steady state flow conditions, we know that it satisfies a Laplacian. Let's remember once again that if k in the x direction is not a function of x, and if k in the y direction is not a function of, or in the z direction, is not a function of z, then we have a homogeneous system. But furthermore, if we say that kx is equal to kz, in other words, we have an isotropic system. Under these conditions, under steady state flow, we satisfy the simplest form of the Laplacian, which is the second of h total with respect to x twice, plus the second of h total with respect to z twice is equal to 0. What that is telling us is that everywhere in this potential field, if I were to obtain the derivative in the second derivative in the z direction and the second derivative in the x direction, everywhere the sum of the second derivative and the sum of the second derivative in x and the second derivative in z would be equal to 0 everywhere once I solve Laplace's equation for a steady state seepage. The other thought that I would like to remind you of is that the concept of derivative, and derivative dy dx is equal by definition to the limit of delta y over delta x when delta x goes to 0. From engineering point of view, we can take some freedoms and relax this very stringent condition and say, well, maybe delta y and delta x and dy dx is approximately equal to delta y over delta x as long as we keep delta x small enough. And this approximation is what we call the finite difference approximation. So the finite difference approximation for the first derivative can be calculated between these 2 points, separated at the distance delta x, and I go and I measure the value of y at the point above and the y at the point below, and that delta y over delta x is a pretty good approximation to the derivative. Now, what is the second derivative? Is the derivative of the first derivative. And so now I have to think of having 3 points, one to the left, one at the center, and one to the right, equally spaced delta x. And now the first derivative is the value of y on the right point minus y at the center point over delta x. And the first derivative for the previous segment is y at the center minus y to the left over delta x. And so the change in the first derivative with respect to delta x is equal to, or is an approximation to, the second of y with respect to x twice. And this is equal to y right minus 2y center minus y left over delta x squared. Now we're going to use this concept to rewrite Laplace's equation in terms of finite differences. And this is going to be equal to, and you can think of, we are projecting this point onto this surface, and so we're going to be looking at points. Let's say the point is here. We're going to look at points above, below, to the left, and to the right, and this is the value at the center. This is going to be equal to, in terms of x, is going to be h total to the left minus 2 h total at the center plus h total to the right over delta x squared, plus we are going to do the same in the z direction, and z direction there will be a point above and a point below, h total above minus 2 h total at the center plus h total below over delta z squared is going to be equal to 0. If we discretize the space such that the delta z is equal to the delta x, so if we do delta z equal to delta x, we can multiply both sides by delta x squared, and the delta x and the delta z goes out, and then I'm going to solve for h total at the center. Notice that I have 2 here and 2 there, so now I conclude that h total at the center is equal to 1/4 of h total to the left plus h total to the right plus h total above plus h total below. And folks, this is Laplace's equation in finite differences. This is exactly the same equation as that one in finite differences, where I have taken the liberty of approximating a derivative by a ratio between 2 increments for sufficiently small increments. Let's see how can we use this equation now to mathematically solve the issue of trying to identify the total field in an area of interest. So we have rewritten Laplace's equation in finite differences, and it tells us that the total head at the center point is the average of the total head of the neighbors, the one above, the one below, the one to the left, and the one to the right. Now we can try to solve a real engineering problem. In other words, we are not going to draw the flow net. We are going to let the computer compute what are the values of the total head everywhere in all the nodes given the certain boundary conditions. So let's start with our typical problem, and we're going to say that we have a concrete block resting within the sediment with a certain head at the entrance, the piezometric head, and there is a certain elevation. So we know the total head at the entry, therefore we know the total head everywhere in this system. If we discretize the system in equal delta x and delta y, because that is what we assume for that equation, so we have created a grid, and we are trying to solve what is the total head at each node on this grid. And we are going to do it in such a way that we maintain delta z equal to delta x to use that equation. Otherwise, we have to go back to the derivation and use the more general version of the equation. Notice that that can be described pretty much as a kernel that looks like a cross. So let's say that this is the center. So we are going to place the cross here. This is the kernel. And I'm going to come to this point and say, what is the total head at this central point? Is the sum of the 4 total heads of the neighbors divided by 4. And this goes everywhere. And I will continue moving this cross back and forth until the values don't change anymore. At that point, I have converged to the solution. There are a few tricks. For example, imagine that you're trying to solve the total head at this point. Well, it will be the average of this value, this value, this value. So we are placing the cross here. But then, what is the value at the bottom? And that is a question mark. And so we can do it in different ways. For example, we can change the kernel not to be a central approximation to the derivative. We can do a forward or a backward, etc., depending where I am on the boundaries. But the other trick is, across a no-flow boundary condition, is to say there is no flow in the z direction. There is no flow across that boundary. That means that ki, which is delta h total from the point above and the point below, over 2 delta z, 1 delta z and 2 delta z's, times area, this is equal to 0. Actually, this is equal to 0 because there is no permeability across this aquitard. But what we're going to do is artificially going to say that there is no flow across this boundary because the total head above and on this fictitious point are the same. So what I actually do is I create a fictitious point which is equal to h total above. In other words, when I come to compute the total head at this point, I'm going to have h total to the left, h total to the right, plus 2h total above, divided by 4, because this fictitious point has the same value as the one above. Of course, I don't need to place the cross at this point because I know the total head on the boundaries, the first and the last equipotential. The tricky thing is to, what do we do where there is no flow across the flow boundaries? The other question is, how far are you going to place the horizontal boundaries? And that is always an important question, and probably if you remember when you draw the flow net, most of the flow is going to come from the near field. There is a funnel that comes from the near field of the barrier and goes nearby, but just to make sure that you don't have boundary effects, you may want to go 2 or 3 times the height of the pervious layer away on each side. And so finally, you can do this by successive iterations, moving the kernel in x and y throughout the system. But you can very easily do it in Excel, for example, where each cell in Excel is actually reproducing each of the nodes here. So you have an equation for each point. So there is an equation here which tells you there is the average of the values to the left, to the right, above and below. You know the boundaries, and you use the Excel solver, and it will rapidly iterate to converge to the solution. I know that this is a very trivialized introduction. There are many numerical improvements that can be done with the proper kernels at boundaries, with the proper algorithms to solve this and to bring this not only to 2D but also to 3D. But this is a very simple and valuable introduction to the problem of a steady-state seepage solved numerically. The last point I would like to make is that If you remember the case of a flow net, and when we are near an intersection, so this is the typical drawing that we do for flow nets in Seepage, and so when we draw the flow net, there will be a large number of equipotentials here because the flow strangles itself, and so the delta x and the delta y will have to be small near constrictions where the gradients are going to be very large. So you need to resolve that with higher spatial resolution in order to properly predict the field of the total energy H total. Be careful at constrictions, equivalent to stress concentrations in mechanical analysis.